Hello friends, welcome to the Formula Engineering classroom, and we are starting the new lecture series of the hydraulic machines, and we will also continue our lecture series that is on the fluid mechanics. So in this lecture series or in this hydraulic machines, first we have to understand a very much important topic, that is the centrifugal pump, and in this topic especially we will discuss about the performance curve, NPSs required, NPSs available, series and parallel element of centrifugal pump. I am discussing this topic here because this topic is very much important from GATE, IES and PSU students who are just appearing for their interviews. The interview panel simply asking about all these things, that is performance curves and NPSH in case of centrifugal pump. So this topic is very much important for that. Okay, so in this topic we will discuss about all these things. So let's start. So when we are trying to understand the performance curve and other things, so first we have to understand some few performance parameters that are necessary to understanding all these things. So the primary performance parameter for the centrifugal pump is the mass flow rate of fluid, is the mass flow rate of fluid, and let I'm denoting this one with m dot. So actually this is the mass flow rate of fluid that is flowing through the centrifugal pump. Okay, so we can write this m dot is equals to rho, that is the density of that fluid that is flowing through the pump, cross section area, and the velocity. So this is the mass flow rate. Now if let we are considering the fluid or the flow is incompressible, so we know for incompressible flow, the density remains constant. Okay, for incompressible flow the density remains constant. So if we are considering a incompressible flow through the pump, in that case the performance parameter becomes the flow rate or discharge, because for incompressible flow as rho is constant, so we can write that is discharge, and this is also defined as the capacity, will be equals to m dot by rho, because the density is not going to be changed. In this case we can write this is area into velocity. So here discharge is the performance parameter for incompressible flow that is flowing through the centrifugal pump. Now the another parameter is the net head, and this is defined as the change in Bernoulli head between the inlet and outlet of the pump. I'm repeating again, the net head, let if I'm saying this is H is equals to net head. So the net head is the change in Bernoulli head between the inlet and outlet of the pump. So let's understand first this one. So let's suppose here I'm considering a centrifugal pump. It's not looking good. Okay, that's okay in the bottom. So let this is our pump we are considering over here, and let's suppose this is section 1 and this is section 2. Okay, so we are considering two stations here, station 1 and station 2. One is at the inlet, another one is at the outlet. So the net head, so net head we can write that is Bernoulli head at the outlet. So we can write this is P by rho g into V square by 2g plus Z at the outlet minus the head at the inlet. So this is P by rho g plus V square by 2g plus Z at the inlet. So net head is the difference in the Bernoulli head between the outlet and the inlet of the pump. So this is the another performance parameter. So first we define the performance parameter is the mass flow rate, and for the incompressible flow we define the performance parameter is discharge or flow rate, and that is the volume flow rate. And the next parameter we defined, that is net head, that is H is equals to the Bernoulli head at the outlet minus Bernoulli head at the inlet. So these are the performance parameter. Now this net head is also proportional to the useful power delivered to the fluid by the pump. I'm repeating again, this net head is also proportional to the useful power delivered to the fluid. Means what? So we can understand this one. Let like this one. If I'm saying that is, if I'm writing the power or that the useful power we are defining, let I'm saying this is useful. Sorry, this is useful power. So we can simply write this is rho q h. So this is not rho q. This is specific weight of fluid to discharge into head. So this net head is proportional to the useful power delivered to the fluid by the pump. Okay, so this one is the net head, and you can see here this net head is including all the parameters. So this part, that is P by rho g, is the static pressure head, and this part V square upon 2g is the dynamic pressure head, and this part Z is the elevation head. So obviously in this case the unit of this head is in terms of water. As I'm using the word in terms of water, doesn't matter what type of fluid is flowing through this pump, but always this head is provided in terms of water. Okay, that is in terms of meter. Now let's suppose if we are saying that is the diameter at the station 1 and the diameter at the station 2 is same. Means if I'm saying let d1 equals to d2, mean the diameter is same. So obviously when the diameter is same, in that case for the same discharge the velocity at the station 1 and the velocity at the station 2 will be same. Yes, and let if the z1, that is the elevation of the station 1, is equals to the elevation of the station 2, that is z2. So in that case this head, that is h, will be equals to, so in this case as v1, that is v at the out and v at the in, it's same, this will cancel out, and this z at the out and z at the in is also same, this will cancel out. So this net head will be present by, this is p out minus p in divided by rho g. So in that case this head is only defining the rise in the pressure in the pumping action. Okay, when the diameter at the inlet and outlet and the elevation of inlet and outlet is same. Now, so as we defined, this head is proportional to the useful power that is delivered to the fluid by the pump, that we are writing WQH. This useful power is defined as or traditionally used as water horsepower. This is water horsepower. Now, so this term water horsepower, again I'm saying it doesn't matter which type of fluid is flowing, this one, this is water or some other fluid, every time we define this is water horsepower. Also doesn't matter what are the units of this power, that is in that case we are defining, in every case we will define as horsepower. So it's not depending on what type of fluid, and it's not depending what type of unit of power. Every time this useful power delivered to the fluid by the pump is termed as traditionally water horsepower. Okay, now there is one more term that is used, that is defined as brake horsepower. So we are writing this here, brake horsepower. Brake horsepower. So what is brake horsepower? So let's suppose here is our pump that I'm drawing here, and here is the impeller eye, and here is the shaft of this pump. Obviously this shaft is connected to some motor, electric motor. Okay, this is connected to some electric motor. So the brake horsepower, okay, so brake horsepower is the externally supplied power to the pump. Means in this case this power is supplied by the motor to the pump. So this is externally supplied power to the pump. This is external power supplied to pump. So this is termed as brake horsepower. So in this case this power is supplied by the use of some shaft power. So this shaft, let if I'm saying, has some angular velocity omega, and this is applying some torque T. So we can say that there is brake horsepower H equals to torque into omega. Okay, this is the brake horsepower. Okay, so now we know what is the power input, that is the brake horsepower, and after some mechanical losses, in this case some that power supplied by the pump to the fluid, that is the water horsepower. So based on this one we can define the pump efficiency. So here we can write that is pump efficiency is equals to the power out, or the power we are using here, the power out is the water horsepower. So we are using this is water horsepower, and the power in is the brake horsepower. So we are adding this is brake horsepower. So this is the efficiency of pump. So the water horsepower is WQH, and in this case this is the shaft power, that is the brake horsepower. This is T into omega. Okay, that is the torque into, that is angular speed. Okay, so this is defined as the efficiency of pump. Now, so here we defined the performance parameter we are using. So first performance parameter we defined the discharge, then second we defined the net head, and third we defined the brake horsepower. Now based on all three, now we are able to understand the performance curve of a centrifugal pump. Okay, so now before going to the performance curve we have to understand two things. First one is free delivery, and second one is the shut off head. This is shut off head. Okay, so what is free delivery? So free delivery is the maximum discharge provided by the pump, and this maximum discharge will occur when the net head, that is H, is equals to 0. So means we are saying that is the, in this case, that is discharge is the maximum and the net head is 0, and this happen when there is no obstruction in the inlet and the outlet, and obviously there is no load on the pump. Okay, so in this case the net head will be 0, and in this case the maximum discharge will occur. So let if I'm saying that if we are drawing discharge as an independent parameter and net head as a dependent parameter, so this free delivery may occur when the net head is going to be 0 and discharge is going to be max. Let if I'm indicating at this point the Q is Q max. Okay, now in this case when the free delivery, that is the maximum discharge is available and the net head is 0, the efficiency is going to be 0, because we know that is pump efficiency is equals to, that is WQH upon TW. So in this case H is 0, so efficiency of the pump is going to be 0. Obviously in this case when the net head is 0, the pump is not doing any useful work, so here the efficiency is 0. Now, so what is shut off head? So shut off head is that in that case the net head H is maximum, and obviously in this case the discharge is going to be 0, and this will occur when the delivery pipe is blocked. So when the delivery pipe is blocked, in that case there is no discharge is available and the head developed by the pump is maximum. So in this case the discharge is 0, so we are on this line, and net head is maximum, so we are marking this point. So this is max here. Okay, in this case also, let if I'm writing here in this case efficiency again here, this is 0 here, so we are saying that is efficiency of pump is 0. In this case also as the discharge is 0, the pump is not doing any useful work, so in this case also efficiency of pump is going to be 0. So there are two terms we are defining here, that is free delivery and shut off head. Okay, now so this combination, when here is the shut off head and here is the free delivery, this will join the line like that. This is join the line like that. So this is the condition. So obviously as these 2 points, the efficiency is going to be 0. So the maximum efficiency will occur between these 2 points. The maximum efficiency, again I'm saying the maximum efficiency will occur between these 2 points. This is shut off head and this is free delivery. So it will look like this one. This is the efficiency of pump. So let if I'm saying this is the maximum efficiency, this is the max efficiency. So at this point the other parameters, like first I'm defining this is Q star. So Q star is the discharge available at the maximum efficiency, and this same line is cutting this curve, so this one, this point we are defining H star. Okay, so these H star and Q star are the operating points at the maximum efficiency, and these H star and Q star are defined as best efficiency points, or we are defining this is best efficiency point simply here. Now if we are taking the brake horsepower, so brake horsepower will look like this one. This is brake horsepower, and at the best efficiency point, this is, let if I'm not saying this is, let I'm saying this is P star. I'm denoting P by the power, so this is the at the maximum efficiency point. So all these 3 points, that is H star, Q star and P star, are at the maximum efficiency, and these points are defined as the best efficiency point. So we can define this one, this point where the efficiency is maximum, is the best efficiency point, and we are writing this is, let I'm saying this is BEP in short. So this is the best efficiency point. So this is H star, this is P star, and this is the Q star. So all these 3 values are available at the best efficiency point. Okay, so this curve we are defining here. Let if I'm changing my color here, let I'm changing the curve of this one, so we can easily understand this one or differentiate from the other things. This one, this is available head. This is head available. Okay, so head available is going from H max to the head at the best efficiency point, and then the 0. This is the head available, and this is for our pump. So now let if we have some piping system and we want to match that piping system to our pump, so that piping system can easily work. So in that case, the requirements of head are defined as head required. So let's first understand what is the head required. So let's suppose here I'm saying there is some piping system, and let it's a different diameter pipe and different length diameter pipe. And let's suppose here I'm defining a valve here. Here I'm defining a valve here. Sorry, I'm defining a valve here. Okay, so this is our piping system. So for this piping system, we have 2 types of losses. That is major head losses, or I think this is H major, and minor head losses. Okay, so major head losses are due to the viscous friction, or simply we are defining this is frictional head losses. This is frictional head losses, and this is due to the fluid friction inside the piping system. Minor head losses are involved, that we can say this is the sudden expansion of the piping system, or sudden contraction of the piping system, or some valves are here, or some bend in the pipe, or some fittings. So all these combinedly termed as minor head losses, and this frictional head loss is defined as major head loss. So obviously in this case, when the flow rate increases in the piping system, so if I'm saying that is Q is increasing in this piping system, so all these losses are also occurs, because that for laminar flow, if I'm defining the HF, so HF is 4FL V square upon 2GD, or we are defining this is FL Q square upon 3D power 5. So as the discharge increases, you can see here discharge here, and this is HF here, so they are square times of proportional of HF. So discharge increases as Q increases. In that case, the HF is also going to be increase here. Similarly, we can explain here, that is with increment in the discharge, H minor also increases. So means with the increment in the discharge, the head required for our piping system is also going to be increased. Okay, because in that case whether we are when we are increasing our discharge, in that case the major head losses increases and the minor head losses increases. So due to that one, the required head loss is also going to be increased. But as we are defining, this is the available head for the pump, and obviously you can see here the available head is going to decrease with the increment in discharge. But we discussed here, that is H required is increases increases with the increment in Q. So it's just opposite of this one. Okay, so if I'm drawing a curve here on our system again, and this is our discharge and this is our head. So this curve is presenting the H available. We are defining this is H available, and let this curve is presenting the H required. This is presenting H required. So in the practical problem, both the curves, that is H available, that is for the pump, and this is the H required, this is for the piping system, are intersecting at a unique point. So this unique point is providing a particular value of discharge that we can use. So for this particular intersection point of H required and H available, our pump possibility are going to be met of our piping system requirement. And as here we define the best efficiency point. So if we are lucky enough, let if I'm saying this is our BEP. So if we are lucky enough, in that case we can get this intersection point of H available and the H required at the best efficiency point. Okay, so but in mostly cases this is not possible. So it is required or it is desired, that is this point, this intersection point is as possible as near the break efficiency point, that is the best efficiency point. Now we can do this one with providing the different RPM, because this performance curve, that is the H available curve, is at particular or desired or designed RPM. So as the RPM is going to be changed, then this curve is going to be changed. So means at the different RPM, it may look like this one. Let if I'm saying this is at the lower RPM here, and this is one is at the higher RPM here, is the more lower RPM here. So it is possible that we are getting a closer and closer point near to the best efficiency point if we change the RPM, or we can use the different diameter impellers for the same casing as we want this one, that is our intersection point of the head available and the head required is going to be near and near to the best efficiency point. Okay, so I think in this topic it is clear, that is the performance curves. We are defining the performance curves are the head, discharge and power with respect to the discharge, and that curves are providing our information, that is at which point the pump will perform best. And I think for the different RPM, obviously the curve will be different, so we can manipulate the values and we can find out our requirement and we can adjust them, and if possible we will also get the required value or intersected value at the best efficiency point, and so this is the best one case for the pumping system. So this is the part 1 lecture of this particular topic, and I will discuss about the NPSs required and the NPSs available and the pumps in series and the parallel correction in the part 2 lecture. And this lecture is very much important from the GATE, IES and PSU into qualified students. So guys, please, I'm saying you have to read all the things about the pumps, and especially when you are saying fluid mechanics your favorite topic in the interviews. So you have to understand all these things because the interview panel is asking as uh, simply asking more about all these things. So best of luck and thanks for watching. And if you like the lecture, please subscribe the channel, comment your doubts, and share the knowledge as much you as can. Thanks a lot.